We've been talking about using integrals and differential equations to solve different problems. Now we're going to apply those in section 6.4. Section 6.4 is on exponential growth and decay, among other things. And the basic premise for this is that in many applications, the rate of change of a variable y is proportional to the value of y. So if we have this rate of change, so a rate of change is with respect to time, the rate of change of a variable y is proportional, so we have this constant of proportionality, to the variable itself, the value y. So when you're given an equation or a word problem that tells you that the rate of change is proportional to the value, then you have this sort of differential equation. It'll also usually be accompanied by some initial value, some y naught, that will help you so that you can find the plus c. Because remember, when we solve these, we would use separation of variables and then integrate. So let's look at this general form and see if we can get a general way to write your equation. So when we separate the variables, we put the y all together, and then we'll leave the k over here with the dt. Once we have that, we know we can integrate both sides. We know that the integral of 1 over a number is the natural log of the absolute value of that number. And the integral of a constant is a constant times the variable. And then we have to have our plus c. Remember, it's really, there's a plus c on both sides, but we can add them together and get one big plus c to deal with. So we have this, and if we want to solve this equation for y, so we know what our y equation is, we know that once we have logs, if we want to get out of the logs, we have to go to exponentials. So the natural log has a base of e. So we have e to the kt plus c equals the absolute value of y. And this, we're going to put our plus or minus out here so we can get rid of this absolute value sign. And we know that we have e to the c times e to the kt. Because when we're adding exponents, we can split it up into multiplying things with the same base. So what we're going to do is we're going to take this and say, well, that is going to be a constant. So we'll just rename that constant and we'll call it a, so that we have y equals a times e to the kt is our equation. But we know that we have this initial value where y equals y naught when t equals 0. So y naught equals a times e to the k times 0, which of course anything to the 0 power is 1. So our y naught is this constant a. So our equation for y is y equals y naught times e to the kt. So when we have exponential growth or decay, what that means is that the rate of change is proportional to the value of what we have. And that gives us this separation of variables, this differential equation, And when we have initial value and the differential equation, we can solve and find that this is our exponential growth or decay problem, our formula, function. K is the proportionality constant. When k is greater than 0, we have growth. And when k is less than 0, we have decay. Because, of course, if k is less than 0, then it'll be negative, which means you'll have 1 over e to the power, and that'll make it get smaller and smaller. All right, so let's try an example. If the rate of change of y is proportional to y, which means that we have this dy dt equals ky, which gives us that y equals y naught e to the kt equation. When t equals 0, y equals 2. And when t equals 2, then y equals 4. What is the value when t equals 3? Okay, so what we need to do is fill this in so that we can figure out what our equation is for this specific case so that we can fill in 3. Well, we know that this y naught is this initial value for when t equals 0. So our y naught is 2. And this other information here is given so that we can find our proportionality constant. So we fill in 4 for y and 2 for t, and we'll be able to solve for k. So we divide by 2. Now, of course, when we have a variable in the exponent, that means we want to go from exponential to logs. So that means we have the natural log of 2 is equal to 2k. So our k is the natural log of 2 divided by 2. Now, most of the time you're going to want to just leave that as the natural log of 2 divided by 2, not put it in decimals, because in decimals you're going to end up with an error. But if you leave it like this, it won't be. So we'll have y equals 2 times e to the natural log of 2 over 2 times t is our equation. Now, you can simplify this down some because we've got that natural log there. So if we split this up, so we have the natural log of 2 times t over 2, and then split that up so that we have e to the natural log of 2 times e to the t over 2. Then we see that we have e to the natural log of 2 power. Oh, sorry, can't do that. I'm confusing myself here. So then we have e to the natural log of 2 to the t over 2 power. Sorry. And this is just 2, right? So we have y equals 2 times 2 to the t over second. Well, this is 2 to the first. So you could simplify it to 2 to the 1 plus t over 2 power. And then there's your equation. Okay. Here we're multiplying exponents. So remember, you can take the base to the 1, and then once you've solved that, then take it to the second one that you're multiplying. So we have this. We want to figure out what happens when t equals 3. So we do y equals 2 times 1 plus 3 over 2. And if we do that, we get that y is 5.657. So when at time t equals 3, our y value is 5.657. Now, there are lots and lots of applications for this. In your book, they give you several different examples: radioactivity, continuously compounded interest, Newton's law of cooling, the resistance being proportional to velocity, the force equals mass times acceleration, equations, and things like that. There are lots of examples in your book. You need to thoroughly read section 6.4 so that you can get all of those examples, because I'm not going to do those on a lecture video when you can read those. The basic thing to remember is if you know that the rate of change is proportional to the value of the whatever it is, the substance or the value of the function, then you start out with this differential equation. And then, as we derived in the first part of the video, that gives you this function for your y value. And then you just use the initial values and things they give you so that you can find y naught and k and get your equations for the exponential growth and decay. And Newton's law of cooling, that uses a similar type expression. It has derives that a little bit on the page 333. But like I say, that's the basic gist of it. If your function is, if the rate of change of the function is proportional to the value of the function, then this is where you start. with your differential equations. So make sure you've read section 6.4 thoroughly and looked at all those examples, worked them out on the paper so that you know exactly what's going on with these different types of differential equations and using integrals to be able to solve them.